Hey guys, so in this video, we will discuss the representations of functions as power series. So basically, our goal is to identify the power series representations of some known functions, functions that we have studied since Calculus 1. So let's start with a quick recall of the definition of a power series. So here, the series of the form Cn times x minus a to the n, where n runs from 0 to plus infinity. If we expand it, this is C0 plus C1 times x minus a plus C2 times x minus a squared plus C3 times x minus a cubed plus so on and so forth, where x is a variable, a is a fixed real number, and Cn's are constants. This is called the power series centered at a, or power series about a. Now, some important remark, the Cn that you see here, it is the coefficient of x minus a to the power n. So the exponent, it's the same as this subscript. Okay? Again, the Cn, it's a representation of some number, whatever it is. But if it is denoted as Cn, then it must be the coefficient of your x minus a to the power n. For example, your c sub 0, it's the constant term. Your c sub 1, it's the coefficient of x minus a because subscript is 1, power here is 1. C sub 2, that's the coefficient of x minus a squared. If we look at c sub 2k minus 1, it must be the coefficient of x minus a with power 2k minus 1. And so on and so forth. So the subscript, the subscript of your c, if you represented all these coefficients as c sub something, the subscript tells you which power of your x minus a it is. Okay? So, now, power series representation. The sum of a power series is a function f of x such that f of x equals c sub 0 plus c sub 1 x minus a plus c sub 2 times x minus a squared plus so on and so forth, whose domain is the interval of convergence of the power series. So recall in our last lecture, we identified where the power series is convergent. Once you have identified that, that interval becomes the domain of your power series as a function. That means we can represent certain types of functions as power series. So like I said, our goal here is to identify some functions which can be written as a power series. Let's start with the familiar power series and of course familiar representation, power or familiar function. This one here, 1 over 1 minus x, the power series representation is 1 plus x squared plus so on and so forth, which is given by this one. Sum from n equals 0 to plus infinity of x to the n. Why? Take note, this is geometric series. Basically, this is a geometric series. And the geometric series, say if r equals x here, you want the absolute value of r to be less than 1. That's what we see here. And furthermore, the power series, say r to the n, and from 0 to plus infinity, this is 1 over 1 minus r. But r equals x. So you get this 1 minus x on the denominator. Therefore, what this means is that if you look at this function 1 over 1 minus x, and the absolute value of x is less than 1, then you can write it as a power series. That looks something like this. Okay? Now, we regard this series here, sum x to the n, as a power series representation for the function 1 over 1 minus x with domain -1 to +1. Take note, if your x, or in absolute value, is greater than 1 or even equal, then 1 over 1 minus x, this is not the power series x to the n. Okay? Again, if your power series, if your x has absolute value greater than or equal to 1, then 1 over 1 minus x, this is not the same as this power series. They are only equal if the absolute value of x is less than 1. Okay? Now, we can use this power series to obtain some more power series. Okay? For example, express 1 over 1 plus x squared as a power series and indicate the interval of convergence. Now, 1 over 1 plus x squared, you can write this as 1 over 1 minus negative x squared, correct? The power series that we just learned, 1 over 1 minus x, this is the sum, x to the n, and from 0 to plus infinity with absolute value of x less than 1. This one here can replace this one so that this one here will be equal to the power series and running from 0 to plus infinity of negative x squared to the power n. Or this will be the sum and from 0 to plus infinity of negative 1 to the n x to the power 2n. And in here, the equality is true when the absolute value of negative x squared, this is less than 1. Again, we have this, or that the absolute value of x squared, this is less than 1, but this is already x squared, so that's strictly positive. But this means that, well, your x is between negative 1 and positive 1. So from this line to this line, you need to recall your functions class. Okay? So again, what does this mean? So for negative 1 less than x less than 1, we have 1 over 1 plus x squared. This is equal to negative 1 to the n, x to the 2n, and from 0 to plus infinity. Next, find the power series representation for 1 over 2 minus x. Again, what we have here is 1 over 1 minus x, sum x to the n, and from 0 to plus infinity. Absolute value of x less than 1. But here we have 2, and we need 1. So we can do this in this way. 1 over 2 minus x, we can factor out 2 from the denominator. If we do that, we have 2 times 1 minus x over 2. So we will have 1/2 times 1 over 1 minus x over 2. Or as a power series, now we can write this as 1/2 times the sum from n equals 0 to plus infinity of x minus 2 to the power n, or we have here 1/2 sum n from 0 to plus infinity of x to the n 2 to the n, or we will have sum x to the n over 2 to the n plus 1 n from 0 to plus infinity, provided that the absolute value of x minus 2, take note this one here, provided that the absolute value of x minus 2 is less than 1, or the absolute value of x is less than 2. Okay? Now, this will be our solution 1. So if I label this as solution 1, there must be a solution 2. Let us look at solution number 2. Now, instead of factoring 2 in the denominator, we can actually rewrite 1 over 2 minus x as 1 minus or 1 plus 1 minus x. We can even rewrite this as 1 minus quantity x minus 1. Which means that instead of looking at x, we will look at x minus 1. So this one can be written as the sum from 0 to plus infinity of x minus 1 to the power n, provided that the absolute value of x minus 1 is less than 1. Or we have negative 1 less than x minus 1 less than 1, or adding 1 on all sides, we will have 0 less than x less than 2. So what does this mean? 1 over 2 minus x, this is also equal to the sum x minus 1 to the n, and from 0 to plus infinity, provided that your x is greater than 0 but less than 2. So notice, This is our solution 2, and this is our solution 1. Still, you got 1 over 2 minus x equals sum x to the n over 2 to the n plus 1, and from 0 to plus infinity, where you got negative 2 less than x less than 2. So let us just write this. So what does this mean? Are they both correct? Well, the answer is yes. They are both power series representations of 1 over 2 minus x, because nothing's violated with what we did. But if you observe this one, the center is at 0. On the other hand, here the center is at 1. The interval when the center at 1, it's from 0 to 2, while if the center is at 0, the interval is from negative 2 to 2. So the same function, different power series with different interval of convergence. Now the point that I want to make here is that if you are given a function, you can actually construct many power series representations by using a different center. And with a different center, possibly the interval of convergence will also be different. Take note that the interval of convergence, it's connected to the center that you are considering. Absolute value of x minus a is less than r. So if we convert this to an interval, that's dependent on that a. So as an exercise, try to write a power series representation for this one, but this time the center is at, say, 2. How are you going to do that? Now for this one, we got power series representation for x cubed over x plus 3. So in here, sorry, x cubed over x plus 3. So in here, we already have that x cubed, and then we have this 1 over x plus 3. If we want 0 to be our center, so that we can multiply this x cubed inside the summation, then we are forced to factor out the 3 here so that we can rewrite it in the form 1 over x minus x over something. Sum x over something to the n from 0 to plus infinity. On the other hand, if we use a different center, we won't be able to multiply the x cubed inside the series because, well, the center for this one is 0. And if the center out from here is not 0, that x cubed will remain outside the summation. But anyway, let us work on the power series representation. So we have x cubed times. First, we can factor out 3. so that we will have 3 times 1 plus x over 3. Furthermore, we need a minus. So here, we can rewrite this as x cubed over 3 times 1 over 1 minus negative x over 3. Which means that this one we have x cubed over 3 times summation negative x over 3 to the n, and from 0 to plus infinity, which is equal to x cubed over 3 times summation, and from 0 to plus infinity, negative 1 to the n, x to the n over 3 to the n. And if we bring in this inside the summation, we will end up with the summation n from 0 to plus infinity, negative 1 to the n, x to the n plus 3 divided by 3 to the n plus 1. But now we need the interval of convergence. Well, we just have the absolute value of x minus 3 to be less than 1, which means the absolute value of x must be less than 3. Right? Now, for other power series representations, we will consider the following set of theorems. First, differentiation of power series. This only tells that you can differentiate power series. If you do that, particularly the power series representation, if you differentiate it, you do it term by term. You do it term by term. Derivative of c sub 0, it's constant, so that will be 0. Derivative of c1 times x minus a, this is just c1. Derivative of c2 times x minus a squared, the 2 will go down, that's why you see the 2 here. C2 is still there, and then you have your x minus a. For the next one, cube, the 3 will go down, C3 is still there, x minus a will have a reduced power. So essentially, you will be able to get this particular form. N times Cn times n times Cn times x minus a raised to n minus 1. And since 0 is gone, your n starts from 1. Now, you can do the differentiation inside the interval of convergence only. Otherwise, well, your function is not equal to that power series if it's outside, right? So you can only do the differentiation inside the interval of convergence. The nice thing here is that the radius of convergence will be the same as in the original function. Right? So in short, the derivative of the power series, it's the power series of the derivatives here. Similarly, you can do integration. You got a power series, which can be written as this way. You can integrate the function, hence integrate the power series. And you can do the integral only in the interval of convergence. So here you integrate c sub 0. You can write it as c sub 0 times x minus a. So you retain the center. You integrate c1 x minus a. That will become c1 times x minus a squared over 2. You integrate this one. This will become c2 times x minus a cube. It will become cube, then over 3. And so on and so forth. And since you are integrating, if this is indefinite integral, don't forget the plus c. Okay? The radius of convergence is the same as the original. In short, the integral of a power series inside the radius of convergence, or in your interval of convergence, you can bring in the integral symbol inside the summation. Okay? So again, inside your interval of convergence. So, from these two theorems, let us find some more power series representations. So in here we have the function 1 minus 1 over 1 minus x squared. Oops. But take note, this is equal to the derivative with respect to x of 1 over 1 minus x, correct? Try to check. Derivative with respect to x of 1 over 1 minus x. This is 1 over 1 minus x squared times by chain rule negative 1. Oh, so there's a negative here, times negative 1. So this one equals negative 1 times the derivative with respect to x of the sum x to the n from 0 to plus infinity. So here, if absolute value of x is less than 1, or this one equals what? Negative sum from 0 to plus infinity of derivative with respect to x of x to the n. But this one now becomes negative sum n from 1 to plus infinity of n x to the n minus 1. Or simply we have sum n from 1 to plus infinity of negative n x to the n minus 1. So again, if absolute value of x is less than 1. Okay? For our next example, obtain a power series representation for Ln of 1 plus x. Now, Ln of 1 plus x, you can rewrite this as the integral of dx over 1 plus x. you can further rewrite this as 1 over 1 minus negative x. You integrate that with respect to x. But this one, you have the integral of summation negative x to the n and from 0 to plus infinity dx, or that you have the summation and from 0 to plus infinity of the integral of negative x to the n dx. Or we can rewrite this as the sum and from 0 to plus infinity of negative 1 to the n integral of x to the n dx. So we brought out that negative there. Which means if we integrate this, we will have the sum and from 0 to plus infinity, negative 1 to the n, the integral will be x to the n plus 1 divided by n plus 1 plus the arbitrary constant c. And in here, this is when the absolute value of x or negative x is less than 1, which means negative 1 less than x less than 1. Now, when integrating power series and power series representations, an additional goal is to find the value of c. So how does this work? When integrating, you need to find that specific value of c. So far, we have ln of 1 plus x equals the sum, negative 1 to the n, x to the n plus 1 over n plus 1, and from 0 to plus infinity plus c. If we expanded this, we will have c. When n equals 0, we will have plus x. When n equals 1, we will have minus x squared over 2. When n equals 2, we will have plus x cubed over 3 minus x to the 4 over 4 plus and so on and so forth. Now, in here, we can take note, absolute value of negative x is less than 1. What we can do is to find the limit, we can let x equals 0. Let x equals 0. Then, on the left-hand side, we will have ln of 1 plus 0. While on the right-hand side, we'll just have c plus 0 all the way. But ln of 1, this is equal to 0. Which means that c is equal to 0. Therefore, the power series representation of ln of 1 plus x, this is equal to the sum, and from 0 to plus infinity, of negative 1 to the n, x to the n plus 1 over n plus 1, where absolute value of x must be less than 1. Okay? So in here, we actually have the power series representation without that arbitrary constant c. It's not really arbitrary. It's something that you need to determine. Okay? Next problem. Use the previous example to find the sum -1 to the k minus 1 over k 2 to the k running from 1 to plus infinity. Let us look at the previous sum. So, copy. Let's just put it here. Paste. So this is what we have. What do you think we should do in order to get this one? They are almost, well, try to observe this particular thing here. We got a -1 with some power k minus 1. We got this -1 to the power n. If we rewrite this one here, this can be written as sum n equals 1 to plus infinity. -1. We have power n and n equals 0. So this must start with n with power 0. So if we are starting with n equals 1, we have to subtract 1 to the exponent. We have here x to the n plus 1. The n starts with 0. The power of x will start with 0 plus 1, which is 1. Here, n already starts with 1. So we will just have x to the n. Similarly, for the denominator. Now look at this. We now have -1 to the k minus 1, -1 to the n minus 1 here. We have power k, we have k and we have n, and both of them starts with 1. What we're missing is the denominator 2 to the k. So what are we going to do? It seems that if we let k, or x I mean, equals 1/2, then we have ln of 1 plus 1/2 on the left hand side. Take note, 1/2 has absolute value less than 1, so we can do that. On the right hand side, we will have summation n from 1 up to plus infinity, -1 to the n minus 1, 1/2 to the power n over n. But we can rewrite this as sum n from 1 up to plus infinity, -1 to the n over n times 2 to the n, which is exactly this one with different counter. So different variable. Instead of n, we use k. So what does this mean? Well, this one, therefore, sum k from 1 up to plus infinity of -1 to the k minus 1 over k times 2 to the k, the exact value of that is ln of 1 plus 1/2, which is 3/2. Or you can write this as ln of 3 minus ln of 2. So that's this particular sum. So notice without the power series representation of a function, this one you won't be able to find the actual value. So what does this mean? I can ask for actual values of series, but only when we know the power series representation, the function representing represent the representation of the function, right? So one last example for this set, and the other examples you can work on them. Find the power series representation of arctan of x. Now, note arctan of x, you can rewrite this as what? The integral of dx over 1 plus x squared. Well, there is a plus c somewhere here, whatever. But let us remove that plus c and put it on the other side of the equation. Then again, this one, we have the integral of 1 over 1 minus of negative x squared dx. But this will be the what? Integral of the sum negative 1 to the n x to the 2n and from 0 to plus infinity of dx. So this will be the integral, the summation of the integral. Summation runs from 0 to plus infinity of negative 1 to the n x to the 2n dx. So if we integrate, we will have the sum from 0 to plus infinity, negative 1 to the n x to the 2n plus 1 divided by 2n plus 1 plus the arbitrary constant c. But then again, we need to find that particular c. In here, by the way, absolute value of x is less than 1, which is the same as the absolute value of x squared less than 1. Now, in order to find the value of c, you just need to choose some nice number. Take note, the power of x, when n equals 0, the power of x will be equal to 1. So this part here has all x, and this is the only constant that you see. Same with the previous example, we can let x equal 0, then on the right hand side that's just equal to c. On the left hand side that will be arctan of 0, but arctan of 0 that will be equal to 0. So therefore I'll just write it up here. Arctan of x, the power series representation is negative 1 to the n x to the 2n plus 1 divided by 2n plus 1, and running from 0 to plus infinity. Absolute value of x must be less than 1. Now, in relation to this, find the exact value of this expression. If you look at this, let us get this one here. So arctan of s is equal to this. So what do you think? What value of x should we use? Well, it seems that this one disappeared. it means it's just x equals 1. So let x equals 1, then the sum, negative 1 to the n over, let us write that nicely, negative 1 to the n over 2n plus 1, and from 0 to plus infinity, so we let x equals 1, this is equal to arctan of 1, but arctan of 1, this is equal to pi over 4. So the exact value of that, of this here, is equal to pi over 4. Okay, so that ends my discussion on function representations of, well, power series representations of functions. We still have some examples in here. You can work on them. Actually, that's just one final example, so just work on them, on it, and that will be a good practice. So that's all for me. I'll see you in our next meeting. Bye.